Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin. I'm going to cover rank and nullity of a matrix, and specifically I'm going to cover the row space and the null space of a matrix A. So let's start here. So let's let A be an n by n matrix. The row space of A is the subspace of Rn spanned by the row vectors of A. The column space of A is the subspace of Rm spanned by the column vectors in A. So we really want to be able to find essentially like a basis for this row space. And we have a theorem that says if an n by n matrix A is really equivalent to an n by n matrix B, then the row space of A is equivalent to the row space of B. So this is going to help us find a basis of this row space. Now, in order to do this, what I need to do is I simply just have to, in order to find the row space of matrix A, I just need to find a row-reduced equivalent echelon form of matrix A, and then the non-zero row vectors are going to be your basis. Because really what it says is that a row space of A is a subspace of Rn. And what I know is that this is a m by n matrix, so we have 3 rows and 4 columns. So you know this is m by n. So it says that the row space is a subspace of Rn, so this is going to be a subspace of R4 because the rows have 4 components in there. So when I row reduce, so I'm going to say B is going to be equal to row reduced echelon form of matrix A, and we can do this by hand or with a calculator by this time of the class. We get 1, 2, minus 2, 0, 0, 0, 0, 1, and then the last row is going to be all zeros, which basically shows us that, you know, row 3 can be obtained by a linear combination of row 1 and row 2. So really row 3 is like an extra basis. It's linearly dependent, so that's why it would be a basis. So it has to be, you know, really the smallest subset of that span, of the span 3 sets, or the span 3 bases. Let's try that again. Yeah. The span 3 vectors. There we go. Okay, so when I find the basis now is going to be, we'll just say the basis of the row space of A is going to be equal to the set of non-zero vectors, which is going to be these and this. So what I have is I have a subspace that has dimension 2. So what we're talking about is we're talking about a plane in R4, you know, a plane through the origin in R4. Now, the rank of A, the rank of matrix A is equal to the dimension of, really actually it's row space or its column space. So if I do find the column space of this, you'll also have 2 linearly independent vectors, and we can just column reduce to do that. You can find your the columns that are linearly independent, and you'll see that you have 2 of them, except they will be in R3 instead, but we'll still have 2 linearly independent vectors because I have 2 linearly independent vectors here. So I'm just going to say the rank of A is equal to the dimension of the row space. You can also say the column space, but we're going to say the row space. So I can say in this case, the rank of A is going to be equal to 2 because I have 2 linearly independent vectors. All right, let's find the basis of the null space and explain what a null space is. Solutions of the homogeneous system AX equals 0. So if A is an n by n matrix, then the set of all solutions of AX equals 0 is a subspace in Rn called the null space of A. This is denoted by the null space of A being all x in Rn such that AX equals 0. So, you know, x being a vector, 0 being the vector as well. The dimension of the null space is called the nullity of A. So, really kind of, in a layman's term, what we can talk about is this essentially kind of being like the x-intercepts of you know, this function a times x. So that's kind of like I said, the most layman's terms of this. So, you know, that set X is a subspace in Rn. So let's find the matrix with the matrix A. Let's find the null space of this. So really, in order to do that, I have to solve, you know, A times X is equal to 0. Now, this is going to be equal to, you know, I have A, which is 1, 2, minus 2, 1, 3, 6, minus 5, 4, 1, 2, 0, 3. And we'll have to talk about the size of X. You know, what is the size of this? Now, what we know is that this is a 3 by 4 matrix, and X is going to be a by 1 matrix. So that means that the insides have to match, so this has to 4 by 1. So this is going to spit out, you know, the 0 matrix. Again, the 0 matrix being a column matrix, which is going to be a by 1 matrix. So we can see that this is going to be a 3 by 1 matrix. So, you know, this is going to be a 3 by 1. And then this is going to be, you know, x1, x2, x3, finally x4, because it's a 4 by 1 matrix. Okay, so the solution to this system of equations itself is a vector space. So what we're going to do is I'm going to write this in augmented form. I'm going to row reduce it, and we're going to find the solution. So what I mean by that is 1, 2, minus 2, 1 with the 0. 3, 6, minus 5, 4, you know, adjoined with 0. So 1, 2, 0, 3, also 0. And then I'm going to row reduce echelon form this. And this is going to help us find the solutions of these things. So 1, 2, 3, 0 with the 0 here, 0, 0, 1, 1, 0, and then finally the last row ends up being all zeros. Okay, so what does this line say? Well, it's still this thing times this x is equal to 0 when we row reduce this. So when I write this, it's going to be, you know, 1x1, 2x2, 0x3, 3x4 is going to be equal to 0. So that's what I have. I have 1x1 plus 2x2 plus 3x4 is equal to 0. The next row says 1x3 plus 1x4 is equal to 0. So 1x3 plus 1x4, I guess I'm going to do 1 there, x4 is equal to 0. And then what I'm going to do is I'm going to solve this for, let's say, x1 and x3 respectively, because they both have an x4 in their in their equation. So I can say x1 is going to be equal to minus 2x2 minus 3x4, and then x3 is going to be equal to minus x4. I'm going to turn this into parametric solutions, so there's an infinite amount of ways of doing this. So I'm just going to do it what I consider the easiest way. So I'm going to let x2 equal s and x4 equal t. So then when I have the solution set, I can say that, you know, x1 is equal to this. This is minus 2. Actually, let's do it this way. I'm not going to change it. What I'm going to say is x1, x2, x3, x4 is going to be equal to this. And you'll see how I'm going to get the basis out of this. So I have minus 2s and then minus 3t. That's from that equation. X2 is just s. X3 is going to be equal to minus t. And then x4 is just going to be equal to t. Now I'm going to separate these into every term that has an s in it. So minus 2s, 1s. There's no s's here, so these have to be 0s, 0s. And then all the t's over here, so minus 3t, 0t, negative 1t, and then 1t. And then when I pull out these parameters, what's going to be left is the basis of this null space. So we can say that the basis of the null space, of a, let's do null, let's say n of a to make it short. The null space of A is equal to these vectors. Minus 2, 1, 0, 0, comma, minus 3, 0, negative 1, 1. Now remember, this is supposed to be a subspace in Rn, which is this, and this is a subspace in Rn. This is a two-dimensional subspace of Rn, so I would say the nullity of A is equal to 2. Now there's an important equation that maybe you could test on yourself, because now you know how to find the row space of this. But what we'll actually see is that n will be equal to the rank of A plus the nullity of A. Every single time. And you could probably see this, that this is a 4. So right now I have 4 here, right? Now we already know the rank of A is going to be equal to 2. The nullity of A is going to be equal to 2. If I wanted to look at the rank of A, remember that this piece of it was the original A matrix, and this was its row-reduced form. So we can see that these two vectors will be your linearly independent vectors for that row space. So I could say, you know, this comma this for the basis of the row space of A, and you can see that there's 2 of them, and that really kind of shows that, you know, 4 is equal to this 2 plus 2. And this equation will be satisfied every time. Sometimes the nullity is 1, sometimes the nullity is 3, sometimes it's, you know, all of them, but this will still hold. So if the nullity was 3, then there would only be one of these up here. So if you like the content, please subscribe.